All right. So, the first thing I guess is to uh, is just to like show the problem, right, of synchronous programming. Okay, and this really comes into play when you're essentially we're waiting for tasks to occur. So a typical example of this is when we call an API. All right, so you can see that here what I'm doing is I'm mimicking calling an API, right? So we have this function called the Foursquare API, and we print, hey, we're beginning to call the Foursquare API. Then we'll wait for the response to come back. Then we'll say it's finished, and then same thing with Spotify, all right? So if we, and let's say it just takes a second to call the Spotify API. So if we execute these functions one after the other, you can see that we're waiting right now, right? We are waiting for the Foursquare call to begin, and then we're waiting for the Foursquare call to finish, right? Because this function executes, and then afterwards, this function executes, right? After this one actually completes, then we execute the second one. So this is typically, obviously, like how we program, right? And our tasks are just, our functions are executed sequentially, one after the other. When you get into like, synchronous program, this is called synchronous programming, right? Or, right, like everything just happens one after the other. So when you get into like the differences between and moving into like asynchronous programming, uh, like you'll typically see these terms. So I just want to like go through these terms of what's like a routine and a subroutine. All right, and this is uh, both routines and subroutines refer to what we've already seen before. So a routine is just our Python program in general, the entire Python program, right? And then the subroutine is each individual synchronous function. Okay, where with the subroutine, before the entire function must complete, and only when one function completes do you start the next function. All right, that's a subroutine. With a coroutine, which is what's happens with asynchronous program, right? Our Python interpreter can move on to other tasks. All right, so what we'll see is, and let me show you this here. So we won't get into right away, like understanding this, but here's the same code implemented with coroutines, right? Implemented in an asynchronous manner. And let's just see what happens. Maybe I can do it. This is a little bit better because it shows you the amount of time as well. So do Python 3 updated index.py. So notice what happened here. Here we did not wait for one Foursquare call to finish before the other one started. Okay? These were 4 calls implemented in a row, and then four square calls finished in a row. It's the same thing if just moving to this code. Here we do the Foursquare and Spotify, Python 3 index.py. I guess I put it wrong. Let's just go ahead and copy this code. So you see this? This time, we don't wait for the Foursquare call to finish, right? We do Foursquare call, and then immediately after, do the Spotify call. Then, at a later point in time, it turns out our Spotify call was able to come back earlier, and then our Foursquare call finished. So, with this asynchronous programming, we can save a lot of time because instead of waiting around 2 seconds for each call to occur, you can see if we like calculate the time that right away we're kicking off 4 calls to the API, and then we wait for each of them to come back. So if it's instead of waiting, say 2 seconds, 2 seconds, 2 seconds, 2 seconds, a total of 8 seconds, here it's immediately execute them, then wait 2 seconds for each of them to come back, and the cost is only 2 seconds and a little bit total, right? So you're saving a lot of time by moving to this asynchronous programming approach, all right? So, and, anyway, what do we talk about? So one was, just to see the problem, right, that we're trying to solve, which is that our Python interpreter or Python program can spend a lot of time just waiting, all right? And we defined and, if we avoid waiting, but rather just move on to the other function calls, then we can, save a lot of time, because instead of waiting 2 seconds for a response, we just kick them all off at once. The other thing we did was we just defined some terms. So the terms that we defined were, a routine, which we said that's our entire program, right? And then a subroutine is a synchronous function call, and then we said a coroutine is what we'll hear for what we'll use for an asynchronous program call. Let's go a little bit, now we'll start to move into how to implement this, and also to understand how to implement this, just how does this work under the hood? So with synchronous programming, right, our program flows sequentially, right? So this is what we've seen, right? Execute one function, then execute the other function, right? We're waiting before we move on. When you do asynchronous programming, the first thing you have to do is create this thing called an event loop, all right? So this is what I'm showing is like, okay, we have our normal program, then all of a sudden we create an event loop. What happens with an event loop is that instead of going one after the other, our Python thread will essentially look to see what coroutine is ready to be executed, is ready to move on to. So I try to show this here. What we'll have to do is really first register our different functions, like call Foursquare, call Spotify, and our event loop will check in on these functions to see, are they ready to be called? Can we move forward with them? I give the analogy in the reading of this kind of being like when we move into the event loop, of kind of being like a waiter checking in on its different tables, right? Seeing are they ready for their order, and going, rotating around the different tables to see okay, are the tables ready to move forward? Okay, so here you can start to see the code, right? This asyncio.run, and then we're passing through this main function. This literally begins the event loop. So this says, hey, we're no longer going to be running one after the other, but rather we're going to start checking in on various functions. So now this part right here registers the functions that we need to check in on. All right. So here we're saying asyncio.gather, call the Foursquare API, call the Spotify API. These are the functions that we want to check in on, right? That we want our event loop to be aware of. Now, to define that this is a function that that this is a coroutine, it does not have to complete from beginning to end. That's why we have to use this async keyword. So it's kind of a combination of both, specifying, hey, these are these functions, that you'll need to check in on, and again, these functions don't have to be executed. Everything has to complete before the next function runs, right? So here we're using this async keyword to define this as a coroutine. Now, inside of the function, right, what we see this other keyword, which is await. Okay, so what await does is it says, if you think about what we have to say is, hey, call the Foursquare API. Then before we finish, maybe we want to do something else. So what we're saying is, while we're waiting for the Foursquare API to return, we're telling our Python thread, you can now check in on other tasks. All right, so await is yielding the Python thread saying, I no longer need you. I can yield you back to the event loop, and now you can check in on other things. All right, so it's okay, call the Foursquare API, begin this. Okay, we'll begin our function. Now we're waiting, and now while we're waiting, we get to move on to the other function and see, is anything else ready? Call Spotify is ready because it hasn't begun yet, so it will check in on calling Spotify, and now this thing is awaited. All right, and again, we go back to our event loop, and it just checks in, and it says, okay, is this thing ready yet? right? It's not ready because maybe it's waiting another second. Then it will go back to Spotify. Is this thing ready yet? It's ready, and it will, complete executing. Then it will check in and see that this guy is ready, complete executing. When both of these are done, then it can move on to the next line of code. All right, then it can move on essentially back to our straight line of programming. So there were really there's a few keywords here, but the main ones that we had to worry about are this async, right? This defines a function as a coroutine, all right? And then the other one is await, okay? So the await is to say, all right, you no longer have to keep executing me, but rather go back to, check in on all of your coroutines, see if any of them are ready to move forward, and, you can execute them. All right. So those were the two main keywords we saw, right? Where await yields back the Python thread back to the event loop. And async is used to define the entire function as a coroutine that doesn't have to operate beginning to end. And then finally, we saw this async io.gather. What this says is, what we saw, this really performs two functions for us. One thing is it registers, right, these functions as part of the event loop. So it says, essentially, if we think about our waiter analogy, it's like these are its tables that it's responsible for. And the other thing it does is you have to wait. The async io.gather says, okay, for us to move on to the next line of code here, we must wait until each of these are completed. Each of our coroutines that are registered here are completed, and then we can move on to the rest of our code. Okay, so it's pretty good just to make sure you kind of understand the flow here. The first thing is, begin the event loop, register the functions that the event loop has to check in on. All right, begin the function calls. So we basically go in a circle, beginning to call the first one and then the second one. All right, hit the await, which means that, okay, now we're yielded back to the event loop. Check in on the next function. This guy's ready. Yield back, call it. Then once we see await, yielded back to the event loop. Check in on the various functions. This guy's going to be ready next. Right, call it, finish it. Again, keep checking. You finish this guy. Now both of these are finished, and we can proceed with whatever is next in our code. All right, we're basically moving back to the synchronous programming style. How did that sit with you all? Yeah, more or less.
When we are in the event loop,
it is good to just think of the terms, be able to explain this, right? Be able to really move through, all right, one step after the other, and think through what are the various steps that are occurring, right? This is a style of program that as we can see is very useful for speeding up our code. Pally, go ahead. I couldn't hear you.
You said it's an event loop, right?
Mm-hmm.
What if there is a bug in the program? It will be hard to then find the bug, debug it, because how do we know which function has an issue?
Well, you'll still see the error, Let me show you.
Use a try catch.
You'll still be able to see the error. Here, we'll just do this. It's first going to. Oh, sorry, this must be the wrong one. Index. Here it's right before it even begins. Right, it's seeing this. But then two. Hold on. Raise. I'm sorry, I'm a little under the weather. Raise exception. Yeah. So we'll still see the error when this occurs. Right? Like once the code gets run, right? Like it still has to run each of these programs right away, or not right away, but one then the other, right? When it's ready, and when it attempts to run it, if there's an error, it will display the error. You know, it will still break. That won't change anything. You know, it can't proceed once it sees the error. It's not like, oh, there's an error, I'm going to move on to the next program. Rather, it's when it hits the await function, right, that it moves on back to the event loop and tries to continue proceeding. So an error will still terminate the program and break it. Other questions about this?
I have some other function which is not asynchronous, like in the same .py file.
Yeah. So after this, right, you can just, print. Let's do this. Sorry, the reason why I'm not running this inside of the Jupyter Notebook is it won't work. The asynchronous code doesn't work inside of Jupyter. But, so remember, this begins our event loop. After we're done with our event loop, we can just proceed, with existing code. Right, so now we're effectively, I'll move this. Now we're done our event loop, and now we'll just proceed with the existing, sorry, I still have this error message. So we wait, we're calling the fall. Okay, now we're done. The last Foursquare call has occurred, right? We've finished our Spotify, we've finished our Foursquare. Now we're done with the event loop, and now we're ready to proceed with the existing code. That makes sense? Same thing below, right? We can, this is our sequential code again, or synchronous code. Right? First, the sync code occurs. Now we enter the event loop, right? And now we're proceeding. So it's kind of displaying, right, this diagram, right? Start normally. It's only really we have to worry about this when we're concerned that our Python thread is going to be going around waiting, right? When we're hitting APIs, things like that. That's when we move into the event loop. Then we're back, process this or, coerce the data, whatever. Where would you return values from these functions? Yeah, okay. So that's an interesting question, right? I mean, there's different things that you can do because, right, like here, it's a little tricky. So I think with gather, I'm not sure how easy that's going to be. Remember, there are other ways that we can kind of store our code. So I would have to look at that to see, like, all right, can we actually collect information from this? But instead, what you can do is you can, write code to a file, like write, our JSON to a file. We could, store this in S3, which is eventually what we'll do. We can, right, save this to the database, right? So it's like call Foursquare API, get it back, save it to the database while we're, but still while we're waiting to get that response back, right? Then we'll, like down here, this is where we can maybe save it to the database, right? So here we're still not waiting for, let me just elaborate on this a little bit more. So maybe here we call the Foursquare API, make a request, we're waiting for the request, move on to calling the Spotify API, right? Wait for this. This guy completes, so now we can immediately then save to the database, something like that, right? In terms of returning the value, I think there is a way to do that. I just don't know off the top of my head. That's a very good question, though. All right. Um, okay, so unless there's other questions,
Oh, okay.
you go ahead.
If I have a question. For example, for a weight, like if you have a, like an I/O intensive task, like like pull like from data from the web, like using some API or writing to disk or something like, so that one like it will kind of yield to the event loop, to other tasks, like if they need to compute something.
Yeah, I mean,
Uh,
one thing to keep in mind it is yeah, you could do that, but one thing to keep in mind is like your computer program. Let me. I probably have to diagram this, right? So the question is, okay, well, this kind of gets into like what's going on under the hood. So you have Python that's operating, and the beautiful thing about like async IO is, well, while we're waiting for this other computer to do something, we'll allocate Python to do something else. Now, so this is another like EC2 or something like that. Like while we're waiting for our API to get back to us, then we can, we have this resource that's just sitting around, and it can move on and check in to see what else it can operate on. Now, if what you're doing is actually, we're running this Python program, and now we're saying, all right, well, what I want to do is wait for writing to other files. Well, what's doing this, right? Python, probably. Like this is the problem. Like that's a little tougher because it's like, okay, well, Python is doing this, so it's not like I have this resource that's just waiting around writing to other files. It itself is the thing that's doing that. So what you could do, there's other ways to solve this, but maybe what you do is you try to allocate this to S3, have S3 pick this up, or not S3, but some sort of AWS resource pick this up and operate on it, right, or some other resource to do it. That's kind of, you can't really use async IO, right, to do this because that is the Python resource still working.
yeah, so kind of if there's like kind of computing like intensive task, like basically you don't want to use await, right? So you want to sequentially execute those codes.
Yeah, I
Like
mean, it's not going to help you, right? Like if it's your own Python thread still working, it's not going to help you. Yeah. Right. I mean, there are, like, that's why you kind of have to be careful about when can you implement. Like, we'll see that, like, in order to even implement this request thing, the asynchronous request, it's not so easy. Like, we're going to have to use, sorry, this is some other code. My apologies. Uh, in order to even implement the asynchronous request, here we're just sleeping, but we're gonna have to use some other code that's like kind of tells Python or some other library that tells Python, hey, while we're waiting for this, we can tell a wait to like that we're waiting to move on, because under the hood. Sorry that this is confusing. I didn't know how deep to get, but under the hood, our event loop it has to somehow say we're ready. Like there's some, it's a little fancy to be able to say, hey, we're ready to move on. In order to do that, you can see we're doing like this async io.sleep because that knows to say, hey, we're ready to move on. We are ready to be picked up by the event loop. Like it has to somehow communicate with the event loop to do that as well. So you'd have to pay attention. It's only like certain functions, like the requests, that you can do asynchronously, like saving to a database. Like, can I just like while I'm waiting to save to the database, can I move on to some other task? Well, it turns out like originally no, but now it seems like SQL Alchemy does have like an asynchronous process, I guess, that like it does allow that to occur. So you really have to pay attention to the library to see like is it implemented with this functionality, right? Yeah. So we're seeing like one very like typical use case, right? Which is like calling request, like, and we'll complete through that. Like, you guys will see, okay, how do I make a request to the API and immediately kick it off, and then be alerted when the request comes back, and the event loop will pick it up and move on. Move on, completing the rest of the task. You know, but not every procedure can you just do that. Right off the bat, right? You have to pay attention to see, like kind of like Google it or whatever, right? Like, how can I implement this asynchronously? All right. Anyway, let me deploy the readings on this tasks to perform. All right. So when you see something like this, right, here we are defining 3 different coroutines. So we're essentially saying, we don't care, because of a coroutine, right, it always begins us with the word async. And that means that we don't care, this thing does not need to complete before we move on to the next coroutine, right? This thing does not need to complete beginning to end before we move on to something else. However, we still do, so anyway, this play game can begin, and before it finishes, we can begin this one and even finish this entity before this one finishes, if it so happens, right? And then same thing here. So these are 3 different coroutines that we are defining. Notice, like, these are essentially objects. They're like blocks of code, and we're defining them already here in line 21, and then we will send them to the event loop, right? Essentially in line 22. All right. So when we define these 3 things, what we're doing is we're defining like a queue. All right. And that queue is really imposed by this word await. Okay. So the word await is really what's like imposing order as to wait. Well, some things do have to occur in sequence. So whereas, this game 2 can finish before game 1, there are internal mechanisms that must occur in order. For example, here we're saying, well, the first round of moves, meaning, player 1 moves and then Larry moves, must occur before round 2 occurs, right? Which must occur before round 3 occurs. So this is like defining that queue. And then inside of each one of these make moves, here's another set of procedures that must occur. So first, we're sleeping for a second, and then we can go back to the event loop. But before that, you can't just move on with. While we're sleeping, you cannot just move on to the next steps here. We're saying this has to occur before anything else follows in the function. Then this has to occur before any of these lines occur. So let me draw this out to what I think may help. This is play game. I don't like this phrase make move. I would prefer it to be like play around, right? Just call this play around. Okay, so now if we're gonna like visualize this queue, the way I would do this is, so we have these 3, so we have our event loop, right? And what we're doing is we're defining essentially, and we're gonna send to the gather function. So to gather, we'll eventually send it, right, these 3 coroutines. Okay, so we'll send gather these 3 coroutines, each of which are play game, right? Play game, play game. These things are coroutines, meaning they're defined with the word async. So we don't care which one of these finishes first, right? Each one of these gets the word async because we don't care which one of these finishes first. Then inside the play game function, we have this like 6 different rounds. I'm only going to do 3 because of space and time, but we have each, sorry, let me erase that. So we'll have play game here. And then here, right, we have 3 different rounds. And then in each one of these rounds, we have 2 different moves, right? The opponent and then Larry, the opponent and then Larry, the opponent and then Larry, right? And then the same thing here. Round 1, round 2, the opponent then Larry, opponent Larry, opponent Larry, right? And then we have this stuff. Opponent Larry, opponent Larry, opponent Larry. Each one of these, right? Remember, there was an await here with, there's an await between each round. And then there's also an await between the first move and the second move, first move, second move, right? So each of these things imposes an order that this move 1, the opponent's move in round 1 has to occur before Larry's response. And then there's another await before round 2. So that means that, we have this sequence of 1 through 6, and then this other sequence of 1 through 6, and this other sequence of 1 through 6. So this is kind of like what we define before we define this queue before we even send it to the gather function. Then we begin, and so what happens is this await gets hit first, right, of round 1, the first move. And while it's waiting for a second, it goes to the event loop to see, like, all right, what's next that it can proceed with. It can't proceed with step 2, with Larry's response, because the word await means, hey, this has to occur before step 2. So it looks at what's next, right? This is what's next, is the play game, right? This is a coroutine, right? Each of these are sent to the gather function. We don't care which one completes first. So it's able to look at this guy and see the round 1 here, and then see the event here that is available and ready. So it completes that. Then this thing says to sleep for a second. And so it looks, right, what's next in the queue. Is this guy ready? So it sees, for the third game, this is next in the queue and it's ready. So it will pick this off and do that. Then it's waiting here. It goes back to the event loop. And it has to see again, of one, this task is ready, this task, or this task. Of these 3 tasks, which one is ready? If this one's not ready yet, it will go check on the next one and then go check on the next one, right? Until it sees one that's ready and then execute it. All right. So, I kept hearing, I guess, when do we need the word await? You need it essentially in I think of it as there's kind of 2 different checklists, I guess, I go through. So one is if you have the word async, right? We have the word async here. You're going to need the word await. So here we're saying, hey, I don't care that you finish this game from beginning to end before you move on to something else, right? You're able to move on to other tasks. So therefore, I'm going to define this as a coroutine. If I define this as a coroutine, you must have the word await somewhere, okay? So this word await is now saying, okay, before you play round 1, before you play round 2, or play any subsequent round, you must play this round. And then we're able to execute this. Finally, we pause here. Before you move on to the next step here, you must wait for, the sleeping to have occurred and to be finished. And then you can continue on with this. All right, so this is imposing that kind of 2 levels of order that I was talking about, where the first await is saying, well, this is for each one of the rounds. Right? This round 1 must occur before round 2. And then the second await is imposing that, okay, the opponent moves. We have to wait for him to move before Larry can respond. Okay? And that's kind of defining at this level, at each level, this set of tasks, this order of tasks that are, this order has to be imposed, but this is a separate set of tasks that can be executed. Did that help at all? Hopefully it helped a little bit. Questions about this or anything to help clarify? Sure. All right. The next thing is, hold on, is basically that, so this is asynchronous programming, and it is a like subset of concurrent programming. Concurrent programming just means that multiple things can happen at the same time, simultaneously. All right, multiple tasks can be happening at the same time, right? That's concurrent programming. Okay, so how can that happen? So I just want to like kind of describe the universe as to like the different ways of doing concurrent programming. Okay, so first, so I'd say there's a couple things. So one, you can have multiple processes. Two, you can have multiple threads on a process, on a single process. And then three, what we're doing is asynchronous programming. These are kind of multiple coroutines on a single thread. All right? So for the multiple processes thing, this really gets into, I mean, one way I think what you kind of have to know is, all right, well, you have your computer, and your computer has a CPU, but what you really care about with it, and this is what actually performs tasks for you, but what you really care about is the number of cores, okay? So, like I think on my Mac, maybe you have like 8 cores. And this is what truly can be run simultaneously, is 8 different procedures can be run at the same time if you have 8 cores. Okay, so number of cores is what determines the amount of simultaneous tasks that can be run, which sounds weird because like you have more than 8 processes running on your computer. But really what happens is, you know, the CPU will alternate between how, and the core will alternate between how it allocates its resource to execute a process. Okay, so it will just switch between them. Now, you can run Python in multiple processes, all right? And the way to do that, there's a couple ways. One, you can use a library to do that. The other thing you can do is just like, you know, have a new file, print hello world, and then you can just run it as a background task. Python 3, if I'm here, yeah, index.py, ampersand, I believe, right? And while I'm, sorry, I probably did not want to do that. So you can run, I didn't want, I wanted just a sample. I don't think I'm in the right folder. Oh, I am, sample.py, print hello world. Okay, so you can basically just run the sample.py and then run a background task by putting this ampersand here. And I guess, I don't know if it's running, I don't know why. And then you can run it again and run it again and have 3 separate processes running. You can also use a library, which like a Python library, which can start different processes. And what that will do for you is that can allow you to use separate cores, if you want, of your CPU at the same time. So you can allocate, you know, and truly simultaneously run different steps at the same time. Different programs. The cost to doing that is that this loads up separate instances of Python for each one of the processes, okay? Which means it loads it up into memory. And because of that, like, you know, I guess there are different estimates. I've never tried it myself, but what I've read is basically like how many processes of Python can you run on your machine? Like it's like 10 to 20, maybe even less sometimes. Right, because this loads up a separate Python library for each individual process. So this actually is not super scalable, okay? And it's because it's loading up a separate Python program for each process. You can also create multiple threads, and again, this is multiple threads on a single process, okay? And for this, what is a thread? A thread is defined as a flow of execution. It is running right from beginning to end, right? That is a thread, and again, you can use a library for that. This asynchronous programming that we're doing occurs on one thread, and what we're saying is, right, while we are waiting for something else to happen, like we're hitting an API, move on to another task, right? So because of this, because we're still just more efficiently using a single thread, we are, this can scale up into like the thousands in terms of tasks or asynchronous kind of tasks that you're running on a computer at a time. Okay, so this is much more scalable than using multiple processes or multiple threads. So multiple processes like 10 to 20, multiple threads is like 100 or so. Why would you use, multiple threads? Well, remember, this kind of gets to, I forget whose question it was, about, well, what if we want to do some sort of like intensive read-write operation, where say we save all this stuff to like a JSON file, but while we're writing to a JSON file, we want to move on to something else. What you could do is you could create, and I don't know under the hood how it's able to do this efficiently, but you could kind of say, all right, well, while we make a request and then create a separate thread that writes to a file, and while this guy is writing to a file, I have the original thread, the main thread, that is now continuing on with the tasks, right? While we're like writing to a file. This does not work with like something like async IO, right? We can't just, if with async IO, what we're doing is we're going through steps, but we're waiting for another machine, right? Like if I say, while we're waiting for a file, do something else, that doesn't work with async IO because we only get one thread, and that one thread is writing to the file, right? So it's allocated. So, what we can do with async IO, right, is we can say, hit another machine, right, make a request, and while we're doing nothing with this thread, go pick something up off the event queue. All right, so that's, it feels like these topics were coming up. I did not prepare to talk about them, but I hopefully this gave some sort of clarification, right, about we kind of have these multiple processes. This is pretty more heavyweight, right? You're loading up multiple instances of Python into memory. You can have multiple threads on a single process. This is more lightweight because it's just one instance of Python that's loaded up into memory, but different kind of programs. And this gets to do tasks like, write to input, output, writing to files. Or you can have asynchronous programming, which operates on a single thread and is useful when we are waiting for another machine to do something, when we are just waiting around, right? Which is normally what's occurring. Question, and these are all instances of concurrent programming, meaning we're performing tasks simultaneously.
I have a question.
Okay.
So, isn't it true that the writing to a file or reading from a file is handled by the kernel? So why couldn't we hand that off to a different process instead of, it's not Python itself?
Yeah, you could hand that off to a different process, right? But I was like, I guess you could handle that off to a different process itself.
Okay.
Just remember, that's more heavyweight. If you're doing that in Python, right, that's more heavyweight. Yeah. But you could do that, this is more lightweight to do it on a thread. I don't know how under the hood it's able to do something like I/O on the same Python process, but I was looking for what is the benefit of using multiple threads on a single process. What can this give us that asynchronous programming cannot? And it seems like that's one of the things, right, is writing to a file. right? Just remember, this is separate instance of Python. This is the same instance of Python, right? Same, like you're not loading up two separate instances of Python into memory twice. So this is sharing a bit more than the multiple processes is. And this is just a single thread, a single flow of execution, right? And this is only when our thread is not doing anything, let's find something else to do, right? That's the idea with asynchronous programming. So it doesn't take up any more space in memory, right? Like, or I mean, maybe it does because of other things, I guess variables or other things you have to keep track of, but like otherwise, no. There's like a PyCon talk that I like that like helped me organize it. I can like put it out into Slack if it helps. Which he talks about this. It's Miguel Grinberg. He wrote like a pretty famous tutorial, and he has towards the end. I'll put it into Slack. He talks about the differences in the beginning and in the end, which is why I just told you about it instead of having you watch the video originally. But like I found the first kind of 10 right here. You see that chess example. He kind of lays out right the ecosystem of concurrent programming, and then he gets into how it works, the async IO library, which you went through. And then towards the end, he gets into that comparison again, right, of processes, threads, and async. Okay, and he talks about the scalability, right, and the fact that, okay, with processes, right, because you're loading so much into memory, you only get like, a dozen processes you can do. Threads, you get more, but async, you get a lot more. All right, so I'll put that into Slack, and if you want to relook at this, you can do that too. Okay. Anything else I can help with this stuff?